Great. Good afternoon, everyone. Welcome along to the second session in our Catapult's Windblades Week series of webinars. I'm joined today by a great panelist, or a great series of panelists from BAYES, the National Composites Centre, ORE Catapult and Bristol University. So if before we kick off, we can go around the table and introduce ourselves. I can start. I'm Peter Greaves. I'm the Principal Research Engineer on blade structures here at ORE Catapult. And yeah, I'll go around in the order that people are appearing on my screen. So Terence, if you'd like to go first.
Yes, thanks, Peter. So my name is Terence Macquart. I'm a lecturer at the University of Bristol. I mostly work on aeroelasticity, previously on aircraft wings and aircraft design. And nowadays, I spend quite a lot of my time developing tools to model wind turbine, analyze wind turbine, and design effectively nowadays better and more sustainable wind turbines as much as possible.
Great. And next up, we've got Kirsten Dyer, who's my colleague here at ORE Catapult.
Hi everybody. So I'm Kirsten Dyer. I'm the Principal Materials Engineer at ORE Catapult, working in the blades team. I've been working here for 7 years now, specialising in blade erosion, but background is in composites. I worked for Siemens and Gamesa for 4 years, working on blade materials before joining the Catapult. And before that, I worked in the aerospace industry, looking after sort of composites and all materials on an aircraft fleet.
And next up is Matthew Bilson from BAYES.
Thanks, Peter. So good afternoon, everyone. My name is Matthew Bilson. I'm Deputy Director at BAYES, and I co-lead a net zero innovation portfolio where we seek to fund the most exciting technologies and accelerate them to make sure we've got the technologies we need to meet net zero in the decades ahead. Thank you.
And finally, we've got Pete Giddings from the National Composites Centre.
Good afternoon, everyone. So I'm Pete Giddings. I'm the Chief Engineer for the energy sector at the National Composites Centre. That means I own the technology roadmaps and deliver all the development projects for the most impactful applications of composites in delivering net zero energy generation. Within wind, that means we're applying those to wind turbines and wind turbine systems.
Great. Well, without further ado, I'll kick off the session. So I'll just share some slides. I'm not going to do death by PowerPoint, but I think it's useful in this case to have something to talk over. So I will just switch that over. So yeah, this is the question that we're asking today in this session. Sorry, I'm just trying to get this to appear. is what is the future of composites in the wind industry?
We're on
So,
your
still
presentation
that,
mode.
sorry. There we go. That should be okay. So, yeah, we've heard yesterday in the first session this week how wind turbine blades have now pushed through the 100-meter barrier, and we know that they're going to continue to grow for some time, and that's driven by substantial reductions in levelized cost of energy that you can achieve by using turbines with higher power ratings. And as they continue to grow, we've got to address new challenges around manufacturing, sustainability, reliability, and of course, cost, which is a massive driver for wind turbine blades. And many of these issues kind of run across all, or at least some of those, or more than one of those categories. So just for those of you who aren't perhaps familiar with how wind turbine blades are made, they're currently put together from a combination of composite materials. So typically that's glass fiber reinforced plastics, which are used for the shells, and perhaps some of the spar caps, which are this is the kind of main load bearing element in the blade here, this box. And typically these spar caps are kind of the heaviest part of the blade, and they're usually made of a mixture of glass and carbon fiber. And for that part of the blade, at least, the performance that's required is extremely high. And so it's unlikely that we're going to see a move away from traditional composite materials in the spar cap, at least in the short term. And that is because they have just incredible properties of sort of high strength and stiffness to weight ratios, great fatigue resistance, and they're also really cost effective for blades, and they can be made into structures that are of the size that are now required for wind turbines. So they are a great material for blades, without doubt, but there's some shortcomings, and one of the ones that's recently come to the fore is that they're not particularly easy to recycle at the moment. So overall, I think it's fair to say that wind turbines are fantastic from the point of view of recyclability. They're mainly made from steel, so the tower and most of the nacelle composite components are made from steel, and that's really quite easy to recycle, and it's very well understood. So the blades are kind of the sticking point here, and that is because it's very difficult to separate the reinforcement, so the glass and the carbon fibers, from the thermoset plastic matrix, which is used to kind of lock the fibers together so they perform as effectively one material. However, as we heard yesterday, there's now several companies that are out there developing matrix or resin materials which can be either uncross-linked or broken down by solvents to kind of break down the matrix and allow the recovery of the fibers, and also the recovery of the matrix, which is kind of going to be increasingly important, because I think in Tony's keynote yesterday for the Windblade Week's webinar series, we heard just the huge quantity of blades that are going out already, and that's going to get ramped up over the next decade or so. So this is going to be a huge problem if we don't figure out very soon how to deal with blades that have come to the end of their life. And we've also got other companies investigating the use of bioresins and wood fibers to reduce the dependency of blades on oil and gas, and sort of reduce the carbon footprint as well. Carbon fiber in particular has sort of a super high global warming potential. So it's almost 3 times as bad as steel. And I'm sure you'll have heard that steel's one of the problem materials as we try to decarbonize kind of everything that we do as the human race. But carbon fiber is considerably worse, but it's also got such incredible properties that it's kind of the only way currently that you can make a blade that's 120 meters long. So yeah, that's a real sticking point at the moment, but there's a lot of work going on in this space to try and allow the use of recycled carbon fiber, for example, and improve the recycling process and also decarbonize the process of making carbon fiber. And all of the big blade OEMs are now looking at aiming for completely recyclable blades for their sort of next few, within the next few years. So the manufacturing process for blades, as we kind of heard yesterday as well, is based on this process called vacuum-assisted resin transfer molding. And that's another area where composites are kind of butting up against the limits of what's possible for blades. As you scale up the length of a blade, everything scales. So not only the sort of the length of the blade, but also the other dimensions. So the maximum chord length is going to get bigger. And also the thickness of the laminates scales as well. So as you start to increase the thickness of these laminates, you can't physically get the resin to kind of travel all the way through the plies that you've placed into the mold as dry materials. And there's an increasing amount of kind of clever work that you can do with simulation to try and predict where the resin will go. But ultimately, at some point, you're going to have to find a different way of manufacturing the blade that doesn't necessarily involve this vacuum-assisted resin transfer molding process. And also the kind of highly manual nature of the job at the moment is probably going to have to change as well. Just we heard yesterday that people in the LM factory are walking they're doing a 10K every day, just walking up and down the blade mold. So as blades get bigger, kind of introducing some degree of automation is going to be necessary. And yeah, I think the other theme that's probably coming down the road is segmentation. So as you can see in the previous slide, we've got different components in the blade. So it's been the way for a long time that we make the blade with adhesive joints bonding together, a suction side shell mold, a pressure side shell mold, often 2 shear webs, and then 2 spar caps. As a minimum, that's kind of the components that go into making up a blade, but they're all made for the full length of the blade. And as we get to kind of 100 meters plus for the length of the blade, it's becoming increasingly difficult to find places where you can build a factory. If you think, you don't just need kind of the length of the tool, you need to have lots of those tools that are all the size of the blade sitting inside the factory. And then you need to be able to get a lorry in there to get the blade out of the factory, and that lorry's got to be able to turn. And the amount of places where you can actually do this is kind of running out. And so instead of building the blade in sort of one part along its length, a lot of people, again, as we heard yesterday, are starting to think maybe we can split the blade up into multiple pieces along the length and have a kind of segmented strategy. And that certainly opens up a lot of possibilities. You can improve the quality control if you're making smaller components. You can open up a lot of different sort of sites for the factories, maybe move the benefits around building blades away from just coastal communities. And yeah, there's a lot of drivers for kind of going to a segmented approach, but it hasn't been something that's so far penetrated into the industry in a massive way. So yeah, it's a very exciting time for wind turbine blades at the moment. I think a lot of the stuff that we've become used to in the way we manufacture blades, the materials we use and the processes are kind of butting up against their limits, and we're going to start to see some big changes in the way things that are done in the next few years. So that, I think, is probably enough from me. I want to make sure there's plenty of time for a Q&A at the end. So yeah, welcome along, and I will now pass over to Matthew for our first panelist presentation.
Thanks very much, Peter, and good afternoon again, everyone. And I'll just wait for my slides to come up. And that's great. Thanks very much. So yes, as I said, I'm Matthew Bilson. I work in Department for Business, Energy and Industrial Strategy. And I co-lead what we call the Billion Net Zero Innovation Portfolio. And I particularly lead on the nuclear, renewables, built and energy storage aspects. And I'll talk a little bit more about this portfolio in a second. So moving on to the next slide. So this gives you a little bit more information about this portfolio. It was announced in the 10-point plan, which the government published nearly about 18 months ago. And that plan was to really set out how the government was going to capitalise on the opportunities from net zero. Of course, that follows kind of the early legislation from 2019, where the UK committed, was one of the first to commit to a net zero target. So within this plan, so point 10 of the 10-point plan was around innovation and green finance. And on innovation, we set up this £1 billion portfolio. And what we do with this money is we look to support companies to develop technologies which are just beyond the current horizon, really. So this is not about supporting existing technologies which companies are already developing. It's about trying to push the boundaries to accelerate the development and ultimately the commercialization of those technologies. And you can see the 10 areas we're focusing on around the edge of that circle. It looks a lot. It is a lot, but we have prioritized which technologies we're focusing on. We're not trying to do everything, even though it looks a lot. And really, the strategic drivers that we're trying to think about in this portfolio, I suppose if you look down, first of all, around the bottom, it's around how do we support heavy industry and industrial processes to decarbonize. That includes electricity, but also for those technologies and companies when processes which can't use electricity, what else could they use, including hydrogen and bioenergy. And then if you move around the edge, going anti-clockwise, another macro driver we're thinking about is around disruptive and radically different technologies. So that includes what we call greenhouse gas removal, and also disruptive, where we are funding very early stage or pretty early stage technology, particularly in young entrepreneurial companies, so spin outs and new to the market. And then round the top, we've got a heavy emphasis on electricity. So those are kind of the three macro challenges we're thinking about, which actually underpins the whole of the government's net zero strategy. So first of all, how to electrify much more aggressively, keeping our options open by supporting disruptive technologies through our innovation portfolio, and also beyond electricity, how do we decarbonize heavy industry and beyond that. So on electricity, just to kind of remind you why it's so important, if we move on to the next slide, this will show you the analysis that was done by the Committee on Climate Change, the Climate Change Committee. So the chart on the left shows you electricity demand from 2020 going out to 2050. Now, the key thing here is to notice that overall electricity demand is forecast to at least double, if not triple. So that's a huge change for our energy system. Is where do we get this big increase in electricity from? And that huge increase in demand for electricity is coming from, I suppose, two or three main drivers. One is electrifying the heat in our homes. So increasingly we will switch from using methane gas boilers to, for our central heating, towards electric heat pumps, possibly hydrogen, but particularly heat pumps. And the other big increase you can see is the purple there, which is transport. So again, switching our cars from petrol driven to electric vehicles. And also right at the top, quite possibly the increase of using electricity to create hydrogen through electrolysis. So those are some of the trends that are driving this doubling or tripling of electricity. So of course, then the next question is, where do we get all this extra electricity that we need? And the government has a multi-pronged approach. Nuclear is in there, but also obviously is renewables, particularly offshore wind, given the cost has come down so much. And the target that the government has set has increased even since this chart was made. This is only done in 2020, December 2020, but it's already gone all up. I think that the original 2020 target was for 40 gigawatts by 2030. That's now gone up to 50. Well, kind of an ambition up to 50. So pretty aggressive targets. So I said the overall drivers are we need to double or triple our electricity. Within that, we think renewables and offshore wind is a key part of where we're going to get that extra electricity we need. And then if we move on to the next slide, so therefore we have chosen to focus on 3 different areas for offshore wind in particular. And this is all about how do we support the industry and the sector to either get over some of the barriers there are or develop slightly different and newer technologies to continue the expansion of offshore wind. So the first of these areas that we're supporting is radar. So we've already awarded just over 3.8 million to about 7 projects. And this is about how do we make sure that the radar systems don't constrain future offshore wind deployments. And we're supporting some different technologies to help the coexistence of large and expanding with offshore wind with civil and military new radar systems. The next program or projects we've got is around composites, which is the theme of this presentation. So I'll talk a little bit more about this in a minute. So I'll skip over that and go to floating offshore wind. And again, we've awarded about £34 million to some floating offshore wind technologies. And this is about how do we make sure that we know offshore wind, fixed bottom offshore wind will continue to expand. Fixed floating needs a little bit more support. So again, we're trying to support different aspects you can see at the bottom there, including dynamic cables, the anchoring systems and foundations and floaters. And within this money, we're also supporting the Centre of Excellence, which is also led by the Catapult. And I would say actually the market, the sector is accelerating even quicker than we had expected. And there's already the policy framework has helped with this around the CFDs, contract for difference, with support for floating offshore wind. So those are 3 areas we're supporting under the renewables part of our overall innovation portfolio. And if we move on to the next slide, I'll just talk a little bit about the composites, this sort of central bit. As I said, what we're trying to do with this program is about innovation. So we want to try and nudge the sort of cutting edge aspects of the sector beyond a little bit where the comfort zone is or what they're doing currently. Obviously, if companies are already investing in areas, then it doesn't need government to also support them. So what we're trying to do is nudge just beyond what they're currently doing. And we think there is a possibility, an opportunity for even bigger turbines, perhaps around 20 or even greater than 20 megawatts. And if that's the case, how do we get there? What materials do you need? And in particular, using different materials. And if you have composites, will it help build these even larger turbines? So moving on to the next slide. And this shows you really what we're trying to undo. So we're trying to unlock the step change in the size of the turbines. In particular, aiming to deliver increased local content and the opportunities for the UK supply chain to exploit that, given up until now the UK supply chain has been slightly underrepresented possibly in the wider expansion of the sector, and to support the manufacturing aspects of how to do it, which again fits within the wider UK policy of direct investment support for manufacturing, in addition to this innovation support. So moving on to what I think will be the final slide, just to talk a little bit more about where we are on this particular aspect around composites. So we've already funded a feasibility stage that was a couple of years ago almost now, which is a modest investment just to test whether we think it was worth putting a bit more money into this composites, including a levelized cost assessment. The conclusion was, yes, we should keep going. So then we've ordered another £5 million to the Catapult and to the National Composites Centre to again continue to work up the engineering designs and the analysis of this opportunity, and in particular work with industry and supply chain to understand again what the opportunities are, what the appetite is in the industry to take this forward. And really the key question we're trying to answer in phase 2 is is it worth going to an even larger program which would try and attempt to demonstrate some of these prototypes. And that work is still ongoing. It's due to finish next summer. And I would very much encourage any companies who are interested or have views on this, please do approach the Catapult and the National Composite Centre about the role that you could play in this program, particularly if you think you've got ambitions to do a bit more. And we'll be making decisions on whether we go to phase 3 probably towards the end of the year and into spring next year while we're thinking about these aspects. So I'll stop there, and I look forward to the Q&A at the end of the session. So thank you very much.
Great, thanks very much, Matthew. We can move straight on to Peter Giddings' presentation now.
Hi, everybody. As Matthew said, I'm Pete Giddings. I'm the Chief Engineer, and therefore I'm one of the people that are helping to drive the dual program, which Matthew's just talked about, through to completion. And I'm just hopefully you can see my screen.
All
Is
good.
that coming through?
Yep.
Fantastic. So at the NCC, we have really pushed hard on composites in wind because we think it's absolutely critical to capturing that market opportunity that Matthew talked about. I'm going to talk to you principally about Suwin, so what we're doing to enable a circular supply chain for turbine blades today, but I'm also going to show how that feeds into the dual challenge and just give you some early insight into the kind of change we're trying to drive, really. But before we do that, it's important just to echo what Matthew was saying, that market size for wind is tremendous and it really is growing. So I've done some work pulling market data from a few different sources, but looking at the value of the UK market and the value of markets which can be served from UK ports easily. Firstly, it's significant. And more importantly, it's growing. Both the UK market and all of those North Sea facing markets are seeing real expansion through 2030 and on into 2040. But this is a supply chain event around composites. So converting that into composites, there are 2 killer facts I'd like to share. The first is that within the UK, just on the carbon fibre elements within the wind turbines, there's a significant annual market size, 166 approximately. But more importantly, and this is something where it speaks to your point earlier, Peter, by converting where our carbon fibre is sourced from, so from China today, majority-wise, across to a low embodied carbon source of energy, either in the UK or some other locations around Europe, it's possible to reduce the embodied carbon in a modern turbine blade by up to 27%, just by your supply chain choices for one of the materials, which is a hugely impactful conclusion that my team have worked pretty hard to get to, but we're going to be working together with everyone else on this call to try and help that drive decisions of operators and where we put our efforts. So coming down into a really important program that's looking to, well, address the imminent issues around recyclability, but also lay the groundwork so that next turbines, future generations, are more recyclable and more sustainable by design. And that's our Suwin program. So just as Matthew said, we're pulling together industry. This is an industry-funded project. Everyone chips in for the collective benefit of having a real circular supply chain that maintains the value within the materials at the end of life. And crucially, for the current generation of blades, Suwin, which is a program supported by OREC, led by ourselves, will be demonstrating at least 2 supply chains for end of life for current glass fiber reinforced plastics during this year. The first will be cement kiln co-processing, and the second will be based on mechanical recycling. Some of you will have seen the report we issued, and that's identified that for the next 8 to 10 years, those two techniques are the viable supply chains for the UK. And all of that is based on a solid evidence base, which we've worked hard to develop with our partners, so informed by operators, informed by the supply chain, and informed by the depth of knowledge at OREC. So we've really built an evidence base, and we're going to keep progressing that so that we can help drive some investment decisions from industry. It's a big opportunity, and it's on us to help people capture that opportunity. So do please come and talk to us. Our contact details will be easily available, and we'd like to talk to you about how you can start working to identify your place in a circular supply chain. Just for some technical interest, recycling can look like a few different ways. Over the last year, we've demonstrated what we believe is first of a kind unwinding of continuous fibers from a carbon fiber epoxy pressure vessel and rewinding those fibers to make a second life pressure vessel. Testing will be in a week or two's time, but that's hot off the press. That's a current solution that we're working up to see the viability commercially. We have worked pretty hard with academic partners to bring together some aligned short fibers, again, from current generation recycling technologies, and we're using the current generation of recycled materials to understand what kind of applications they can be put into. In this example, we used a second life material from an Airbus aeroplane and turned it into a wheelchair ramp for a national rail network in the UK. So it's starting to be a real sector, but it's one that needs a lot of support, and we'd really like to discuss with people how we can help you make it happen. So bring it back to future turbines, and I want to put these two programs on the same slide. The Dual Challenge is explicitly targeting the use of resins and design principles developed within Suwin. So when we design future composite components, we are doing so that's more sustainable than what's done today. And so the turbines they go into are more sustainable as a result. So as Matthew said, the vision for the Dual Challenge is to use novel, transformative composite technologies deployed into a large-scale floating wind turbine to reduce the LCOE, to enable a step change in turbine size and therefore get more electricity per turbine and increase that AEP, and crucially give a good reason for businesses to invest in the UK, to grow the UK content in the turbines that we install in our own country, and hopefully help us capture market share of turbines installed in other territories. So what that's actually looking like is the turbine model early stage on the left-hand side, a floating 20 megawatt unit with composite design solutions tested and simulated for shaft, tower, blade, and hub. Those business cases are developing, the designs are progressing, but really what's the most important thing here is we cannot do this alone. OREC, NCC are really committed to bring the best intelligence from industry in to help us develop this, so we're ready to move into phase 3 and we can demonstrate to Matthew and to the government that there's real value for UK supply chain in attempting something really brave, but that has the potential to significantly decrease mass, significantly increase the profitability of operation of large wind turbines, and that we believe is doable. We believe this is doable in the UK in a time frame that supports deployment. So we're really excited by this, and all of the work that we've done in partnership with the University of Bristol and OREC is going to be underpinning for the success of this program, and we hope will contribute to the success of the industry. With that, that's the end of what I have to share. Hopefully Terence will pick up and explain what's coming next from his side.
That's great. Thanks very much. I thought particularly the unwinding of composite pressure vessels, that could be a real game changer. If you can get continuous fibers back from a recycling process, then suddenly you could start seeing properly recycled blades back into blades, I would say. So yeah, very, very interesting potentially in the long term.
Yeah, all the strands are coming together, Peter.
Yeah, beautiful pun. Yeah, no pun intended, I'm sure. Terence, on to you. Let's see what.
Right. Can you see my screen all right?
Yep, looking good.
Yeah. Okay. So thanks, Peter, both Peters and Matthew, to kind of prepare the scene for me. So as I said, I'm a lecturer at the University of Bristol, and I've been kind of working closely, effectively with the offshore energy Catapult and the NCC over the past few years, basically now to develop tools to kind of help address some of those questions. So my presentation will be a little bit more technical than what you've seen so far, and maybe hopefully will give you an idea of how we're trying to actually practically address some of those challenges. So I've titled my presentation, How to Improve Wind Turbine Designs for Better Performance, and obviously, quite importantly nowadays, for better sustainability. So this has already been told a few times already today and yesterday. So wind turbines have been increasing to decrease the LCOE of the turbine, and that's a trend that we're likely to continue to see. To make the energy more competitive. But that obviously has led to the fact that turbines are now very large, very flexible, and therefore, we need, as Peter said, very strong materials, and that's where carbon comes in. And we are unlikely, as long as we keep with three-bladed upwind wind turbines, to move away from this need for very strong carbon-type materials, for which there is no current good alternatives. So the problem, obviously, as we've already mentioned, and I think most of you are aware, that composite blades are kind of one of the final hurdles really towards, in theory, fully recyclable blades. And if you have seen the couple of pictures posted by Bloomberg's recently, then it kind of gives a relatively bad press image to an energy that otherwise wants to show itself as green. So this is something that obviously has a lot of incentive to kind of move away from this kind of landfill ideas, and also because there's a lot of, as Peter mentioned just previously, there's a lot of actually value in the carbon stored in the blades. It would make a lot of sense if we could try to kind of recycle somehow those blades, lowering cost, but also changing the image of the industry as a whole. So some of the challenge that we have, obviously, that we already talked a little bit about, is that large blade need typically large quantity of carbon or glass fibers, reinforced plastic, and those are typically difficult to recycle. So a couple of research questions that one might answer is, can we devise effective recycling processes? And that's kind of what the NCC has been really looking into. And a question that I'm perhaps more interested about, and what I'm going to talk about here today, is, can we design turbines perhaps differently to improve that sustainability while still remaining competitive in terms of energy output? So how do we design more sustainable wind turbine? Well, you might think at first that obviously using different materials, we could start from there and simply, let's say, replace the carbon by other glass, by flax, other types of natural fibers, and then basically we know, at least there's been enough evidence that some of those materials have enough, let's say, structural properties to replace glass. Yes, carbon, not to my knowledge today, but obviously if we could replace glass, that would already be a good thing. And those could have less, let's say, impact on the environment. But obviously, if we just study the material on its own, then it doesn't really give us the full picture or the full story, because as we replace the material and maybe calculate, the embodied energy in the creation and manufacture of that material and its potential harm for the environment, whatever you want to call harm, there's so many definitions for it, then we're actually looking at a very small size of what we need to when we need to look at the wind turbine as a whole. So what we really need to do is say, okay, if we want to change a material, for instance, we need to be able to say what's going to be the effects of changing this material on the components on the turbine as a whole, for instance, on the blade, on the tower, and on the platform wind-up. And so we need a way to basically have this analysis modeling capabilities that goes from the material definition to the full design of the turbine, with possibly inclusion of how do you manufacture, and is there, for instance, a supply chain capabilities for this, let's say, natural fiber materials for operation, repair, decommissions. Some of those capabilities are really good at the NCC, where they can assess these supply chain possibilities and our Catapult. I have been focusing mostly on component design and providing those capabilities to both ORE Catapult and NCC. So what does those capabilities look like? So those capabilities look like a software that we have developed at the University of Bristol over the past few years with collaboration with ORE Catapult, of course. This software is called Atom, and effectively it's an aeroelastic turbine optimization method. It's a fancy word to say that we can model wind turbines in the current complexity to a relatively high level of fidelity, analyze them. So basically, model a wind field, see how the wind turbine deform, experience the stress, or find out the stress experienced by the wind turbine, the loads, the deflections, and so on, and kind of determine whether or not the turbine is feasible and its performance and so on, in a relatively short manner, which is obviously very important for design purposes. Then we basically, once we have those analysis capabilities, so basically a massive, let's say, code, if you wish, that allows us to capture the aerodynamic properties of the turbine, the structural properties, its cost, as well as its control properties, then we kind of wrap all of that up into what we call an optimization method. In short, this is simply a tool that allows us to start from a certain design of the turbine, and then from that design, try to find a slightly better design. And it keeps repeating that process on and on until you find basically the best design that you could from a given configuration. That's a little bit more complicated than this in theory, in practice, sorry, but in theory, that's the idea. So what we can do with this is, so far, the focus of the industry has already been, and still is to some extent, on the reduction of the LCOE, and that's what we have been using these tools a lot for. But with the current shift towards, obviously, the need for more sustainable wind turbine, then what we can do is we can perhaps change this levelized cost of energy measure that we have been using so far for perhaps a bi or multi-objective optimization, or meaning that we could simultaneously try to minimize the LCOE, but also take into account sustainability. So typically, Atom, what we're trying to do with this software is to kind of allow earlier on during the design process, basically a bit more design confidence. So, but also reducing the number of evaluation needed to evaluate new concepts. So, for instance, if you want an alternative new material for your turbine, what does the turbine is going to look like as a whole? Is it going to be feasible? And what's going to be its overall impact, not only in terms of performance, but in terms of environmental impact? So a couple of case studies we've built with our partners over the times are this 15 megawatt wind turbine redesign, which basically we took the in-wind design, which was an open source available 15 megawatt design in the literature, which was not so good, which is not so good really in terms of the way it has been designed structurally. And so basically what we did is kind of we re-optimize it to be much more close to, let's say, structurally feasible and sound design that now the ORE Catapult, the NCC can use as baselines for other studies. We have done the same as Matthew mentioned for the 20 megawatt design. So we have basically used the same process to build a relatively 20 megawatt rotor and kind of extract trends that we can see in the blades. And so typically what we're seeing is we keep going towards more slender, so like basically thinner types of blades, perhaps rotating a little bit faster than the counterparts in order to reduce the loads, but also to possibly remove a bit of carbon. So this is also why those design tools are important, because they can allow you to basically kind of change, let's say, the load, therefore the geometry, and therefore the amount of carbons that you need to do to build the blade. And one way to basically be more sustainable would be to use less carbon if we can, if we have trouble to recycle them in particular. As I mentioned already a couple of times, so Atom has been used already by the Catapult and the CC in a couple of different projects, typically to develop different types of baselines and to try to, let's say, either minimize the LCOE or in Suwin to kind of currently being used and on an ongoing project to try to, let's say, evaluate the impact of, let's say, alternative materials on the overall system level. So a couple of future work, and that will be my last slide for today, will be obviously to kind of, a couple of things that we're trying to do is obviously to move away from this LCOE focused design and obviously to move towards, let's say, multi-objective optimization or design strategy, where perhaps, you know, it is envisageable that we could reduce the LCOE a little bit to increase the environmental, or to decrease, sorry, the environmental impact. The truth is, this is not a simple line in practice. This is quite a complex, multi-dimensional landscape. And at the moment, I don't think anybody has a very good idea what that landscape look like for sure. Obviously, one of the things we can do, and we're already doing, is trying to use this software to kind of assess alternative material, but not at the material level, but obviously at the component level, at the system level, in order to create ideally greener, but still very performant, competitive designs. That is all for me. Thank you very much, and hopefully I haven't taken too much time of my 10 minutes.
No, I think we're right on time, really. So yeah, that was really interesting as well, Terence. I think now we can throw it out to the audience for questions. So if anyone has any questions, just pop them in the Q&A box. Not seeing any just yet. So I did have a few that kind of cropped up as we went through there. Particularly from Matthew. I was wondering if there is, I won't press you for like a hard number, but is there a kind of rough ambition for the number of jobs that you think could be created in the composite sector in the UK?
That's a pretty big question, Peter. I think I'm
Agreed.
not sure. I don't know what the exact forecast is at the moment, but I think yes, I think the ambition is if we think it's a growing sector which has real traction, then obviously we want to see it expand, particularly as environmental aspects and embodied carbon issues perhaps start being considered a bit more fully in the years ahead. I think there will be more consideration about how we shift the sector to more employment in those areas.
Great. Good stuff. Yeah, so I don't see that we're getting any questions through just yet. So I don't know if we maybe want to discuss the fact that there's been, and rightly, I've been kind of thinking for a long time, having worked in this industry for kind of 10 years, that it's taken quite a while to get to this point where we're having the main focus of sort of panel session be on sustainability, and that's great, but we also need the performance. So I was wondering perhaps, Kirsten, if you've got any thoughts on the prospects of kind of increasing the performance of composite materials rather than just the sustainability.
Yeah, so I think so I was at like a sort of blade materials conference this year, and the feedback that was coming from the OEMs is very much they actually to design and manufacture the next set of turbines, they actually need stronger materials. So for one, I think that's going to be some developments going on with the glass and carbon manufacturers to develop new glasses, to get better properties out of the materials they've got already. I mean, we see that happening with glasses, with the H glasses that have been developed for the wind industry. But I think the other is actually in terms of the incorporation and how they're used. So, for instance, a lot of fatigue performance can be created by looking at interfacial properties. So actually developing strength through the integration with the resin systems. We see them moving to pultrusions, for instance, and a lot of people using pultrusions, they're using the composite manufacturing processes that they have to sort of maximize the strength. And I think that's an area that can be innovated. And then one area that we're working on is actually trying to use recycled fibers and create a manufacturing process based on sort of current technology of sort of fibrous mats, but actually creating, using that process, a sort of a mechanism for like functional grading, and these mats will be used to incorporate an adhesive. So instead of your blank strength of current incorporations of sort of glass particles and things like that in adhesives, we'll be creating this mat that gives you your strength properties where you need it in a clever manufacturing and design process. And that's potentially a way of actually using sort of recycled glass from blades and actually putting them back into the next generation of blades as an increased like adhesive with improved strength. So we need to be clever, I think.
No, that actually leads quite nicely onto the next question, the talk of adhesives there, because we've had one question come in on ideas on assembling segmented blades in the field rather than at the manufacturing facility to kind of ease the logistical strain, which I think is something that came up a bit yesterday as well with the LM presentation. They were talking about a segmented blade that was assembled for logistics reasons. Yeah, I think adhesives tricky in the field, and probably we'd all agree on that. Like they need to be very well controlled, those processes when you're bonding, especially stuff the size of blades together. So yeah, I think the segmentation in the field is probably going to stick with being mechanical joints for the time being, but we've done some work in the same project that Kirsten was just talking about there, around sort of, can you do a segmented joint anywhere on the blade? And it looks like with an adhesive joint you could join anywhere along the length of the blade. It's feasible, but with a mechanical joint you're kind of restricted to perhaps a bit closer to the tip, because the middle section of the blade is kind of seeing so much load relative to the size of the cross section that it's just impossible to do with a mechanical joint that's not ridiculously heavy. So don't know if anyone wants to weigh in on that one as well.
Yeah, I mean, so we have a PhD student that's actually looking in this kind of segmented blades along the span, and I think, yeah, as Peter says, it's difficult for a very heavily loaded blade to first create a joint that's reasonable. The issue, and people are looking at manufacturing, trying to assemble on site, but the issue is typically, yes, you might not have the degree of certainty, let's say, about your manufacture as much as you would have on assembly floor. And it's all about how fast can you go as well, because typically adhesive, if you have an adhesive, then you're going to need time for curing and everything on site, which again might not be very easy to do. So at the moment we're looking more at a combination of mechanical / adhesive, but there's no as far as I know known good solutions to tackle that problem.
Maybe it might be useful to share some experience of qualified composite joints, subsea, and qualified composite joints in aerospace, which are both bolted. I don't know of any primary structural joint in aerospace or oil and gas which is solely bonding, and I don't believe that's going to be feasible for wind turbine blades in the medium term, maybe even in the long term, without some real changes in the way we design and adhesive properties. So I think I'm basically, Pete, I'm agreeing with you. I think it's going to be mechanical joints at the tip. I'd also question how big of a problem the logistics are for offshore blades. Onshore, 100% agree. But for offshore, there are no roundabouts to get around in offshore blades, just wide open sea.
No, this is true. Yeah, I think the kind of trick with the adhesive joints might be that you kind of enable the quality control that you need to get the correct bond line thickness and stuff by reducing the segment size, but you're still going to be dealing with a huge structure. Like even if you break the blade up into sort of 10 sections, which is kind of pushing the limit of what would be seen as remotely plausible, I would say, you're still going to have the chord length might be 9 meters on at the biggest point on a 20 megawatt blade. So you're still going to be dealing with a huge structure. And I think getting that control on bonded joints means, yeah, it's going to be maybe tips. And yeah, agreed, like the logistics is definitely less of a problem offshore.
I'd just like to add my experience from aerospace. So one of the jobs that I did when I first started was basically in aerospace, if they manufacture like a repair on the aircraft fuselage, then they have to actually create test specimens to qualify the strength of the adhesive joint. And literally, they use the strongest adhesive, and the variation that you can get from the different people actually manufacturing the test pieces range from some people creating the datasheet properties to samples that fell apart in my hands. So that's another issue that is going to be huge for segmentation and manufacture on site.
That sort of pushes you towards automation as well, I think, doesn't it? So yeah, that's just so there's time for this other question that we've had. Carbon fibers will retain quite a lot of strength after recycling, but what about glass fibers? It says, does the process you develop retain most of the original fiber strength? I'm not sure which process it is specifically, but maybe generally, what are the properties like after you have been through one of these recycling processes?
So that's something that I can cover pretty well. So Pietro, thank you. That's a great question. Carbon fiber only retains a high fraction of its tensile strength in a few processes, but yeah, you're right, in some processes it does. For glass, on our assessment of where the literature is today, it's quite variable, honestly. But without being slightly slippery, that's the wrong way to look at it. What matters isn't the retention of tensile strength of the fiber, it's what properties the second life material has. So, you know, Terence and Kirsten's nodding, which is good. We need to be able to transfer a recyclate out of a recycling process, which could be 50 mil shards. It could be continuous fibers one day, but I can answer your question better when we're looking at a molding compound made from recycled material, when we're looking at injection molding compound, when we're looking at a second life laminate. That's what really matters. And to be completely open with you, almost all of the academic literature, and we're only just starting to correct that, doesn't deal with this well. We give in single fiber tests, residual values for tensile strength, which bluntly doesn't really matter that much. I mean, being genuinely honest, you have to be able to convert that into a usable material in the second life, and the industry isn't there yet. So we'll lose some strength in the fibers. Much bigger question is, how long are they? What's on the surface? Can we get the adhesion into a matrix so that Terence can tell us whether we make better components or not? It's a different way to look at things. We're turning from material science and turning it into materials engineering. That's how we create value. That's how we deliver jobs into Matthew. Not his team, obviously, but that's what we're trying to do here: create a viable industry. I don't think that's just me. I should get off my soapbox and let somebody else speak.
I agree with everything you said totally. That's and this is why we started this adhesive project. What it's currently filled with, like ceramic particles, like talc. So we're not looking for the glass strength. But it's actually by incorporating fibers, and it's actually the fibrous nature that we're interested in, because that gives us certain properties. So more reinforcement with actually like less material. So we have to look at it exactly, as Peter said, we have to look at it differently and use the recyclates in new ways.
Yeah. So circular doesn't mean, from blade to blade. Is it going to be from blade to another second life and possibly third life and so on?
Yeah, I agree with that. I think it could mean potentially one day from big blade where the properties are all really, really required to smaller blade or something like that, because I think they didn't have these properties when they're making kind of blades in the 90s that we're working with now. So maybe we can one day get to the point where we can make super cheap blades with just not quite so good properties. But yeah, I think it's right to think in terms of other industries, how can they use the stuff that we're, because anything is better than what's happening at the moment, really. Like anything's better than landfill, really. Some kind of value back from the material at the end of life. So I think we're on 2 o'clock now. So as we don't have any more questions currently, I will call the session to a close there and just say thanks once again to our panelists, and I hope you've enjoyed it, and do make sure you join us through the rest of the week at, I think, the same time, but probably double check that for the remaining 3 sessions. Brilliant. Thanks very much, everyone. Have a good afternoon.
Thank you very much. Have a good afternoon.
Thank you very much.
Cheers, everyone. Bye.
Bye.